Hello, gentle readers, fellow Earthlings. Today in Reading Foundations, November 30, 2025, we'll be following on to the stellar exotics about the notions of all the stars in the sky, each one distinct, unique, yet somehow alike as far as we can tell. The macro scale. Then today would be more of the exotic, the particles, the micro scale. Since each of these represent the standard kind of idea, standard candles, say, and then the standard model of physics as it's so purported to be, the plan in a sense, or the commonality as it may be, that then the exotics represent these other branches. So in the 50s and 60s and 70s, the 1950s, 60s, and 70s, the 20th century, the particle physics after the development of atomic theory, then nuclear theory, and as for quantum theory, then had that in the experiments of the accelerators and the linear accelerators and the ring cyclotrons mostly, and the cloud chambers and some of these other apparatuses of the high precision experiments of the experimental physics for a theory of particles and waves, that there was a great proliferation of all kinds of concepts and ideas to help to try to explain all these observed interactions. And so this, for example, gets to the great difference between the theory of nucleons and the theory of quarks. So then and then the quarks association attachment to the standard model of physics. And then the idea, though, that as a branch that they may be, that is considered and picked to be kind of the principal branch of the physical model for the mathematical model for the physical interpretation, mathematical interpretation, all according to our rather modern language of science and physics and mathematics. That the standard model isn't so necessarily any more or less qualified to be the standard for these things among these considerations, the concerns of these tetrads of quantities and forces and fields and elements, than is with regards to these kinds of things. So kind of like the talk in Reading Foundations here about the E-energy and F-Lorentzians, or like the Einstein's notion that, or as of from the time when the photoelectric effect equated photons and electrons, and why that became just a very simple and clear way to equate these matters of conservation and continuity more thoroughly, that the charge to mass ratio of the electron was the only thing that was really measured. So it's kind of always is set up as this sort of tent of these quantities together to arrive at how then any particular view of it is as yet as if seen as a point in perspective and projection. So for the running constants of these kinds of things, that the charge to mass ratio of the electron to the and as regards to the proton, then to define things like stoichiometry for chemistry, and as after the electron orbitals, of course, and the very well grounded and quite thoroughly understood theory of the atomic model that results. And as mentioned here, that the structural chemistry gets above that, the molecular chemistry gets above that, and why the theories of bonds and so related, and for Heisenberg and the uncertainty and the orbitals and the position of the electron, and that the charge to mass ratio as of a quantity, both a combined quantity and as of its derivations all these different ways, and that the induced potentials that so arise result making a perceived force according to measurement and these kinds of things. That the standard particles and exotic particles and standard candles and exotic candles of the microscale and macro scale here are something that is just kind of introduced then, as that's just kind of the context of this conversation. then the idea of the energy and the fields, and the energy in the entelechy, and the fact that there's all these different kinds of ways to formalize mathematically to make for a Lorentzian, which is just a system of these second order partials, so that anything third order and beyond is just kind of gone. It's just, it goes to zero in this partial differential equations, these things. And it makes for the quadrature, this like, well, then at least locally, everywhere there's a coordinate origin, there's a sort of square. And this metric and norm making for straight lines and right angles. And then for the affine and geometry, preserving all these matters of form and proportion. Then for things like parallel transport, the ideas of the soliton and the instanton is different than the particle at all, yet at the same time the same thing. The wave packet and these kinds of ideas all have to kind of eventually kind of get stacked on top of each other, because otherwise the data would refute the otherwise the theories of these simpler things together. Has it then the deconstructive account is kind of like pull that back apart again and see why it results kind of a great circle of the things, so that the sum of potential is kind of deemed, since Lagrange and the Lagrangian, and what makes for both the severe abstraction and as well as like that everything else is still the virtual above that, and it always gets added back into it for that to make a zero, to that to make a starting point, as that's also the end of the things, is the classical and the linear and the point and the particle in the middle. So it's rather involved. Yet at the same time, it can be considered as like, well, just think of it as a sphere or a box from the outside, besides this from the inside. So it's just complementary duals again, and a lot of the different notions and concepts that regularly arise is from these discussions. The moment in motion after the descriptive differential dynamics, which is really just trying to get an idea of the original analysis and how to deal with the matters of the origin and the identity dimension itself, and the infinitely many higher orders of acceleration which formally exist, nominally non-zero, in all infinitely many higher orders, any kind of real change at all, this kinds of things, to the moment in motion in the world's turn bit, about the potentialistic and about distinguishing the space-contraction-linear and space-contraction-rotational and frame spaces and space frames, to make it so why then that theories then picking a branch, picking a point, picking a perspective, like relativity theory of Einstein, saying there's no absolute motion, everything else being absolute, then for just giving the free and fixed as of out of that, here is that there's kind of a naturally one of those implemented by physics reality itself, the fixed and free information about the energy and entelechy, that's nominally or that meaning at least in its name, vis-a-vis in name only, the Entbergung and the Nakbat of these things, that is naturally the physics and the reality. And that it meets all our principles of paucity, meaning efficiency, or the least amount of explanation necessary to attach to these things for the causality, and then it can still be just a one world hypothesis and a clock hypothesis, making for the strong mathematical universe hypothesis that's yet a continuum of the infinity of things, and not just an incomplete, at best, self-consistent theory, but overall the true theory is the one true theory of the things after strong mathematical Platonism and strong logicist positivism, strong mathematical universe hypothesis, fulfilling all the requirements and desiderata of the idealistic traditions of truth, and then also for science and reason and the empirical intersubjective equi-interpretability of things, to arrive at least one good theory, a theory. So I have this book here. It's called Exotic Atoms 1979. And so Fundamental Interactions and Structure of Matter, edited by Kenneth Crowe, Jean Duclos, Giovanni Florentini, and Gabriele Torelli. From the Ettore Majorana International Science Series editor Antonino Ziccici, Physical Sciences. So Majorana is kind of associated with the Majorana spinor, and so then that's the mathematical devices after reflections and rotations, and Cartan is geometrical, yet helping to show the convolutional setting of exchanges and these kinds of things, symmetries. Then Majorana is like, oh look, I found a little leaf off of that's not the principal branch of the spinorial setting. And then it's like, well, let's make an experiment to determine that exists. And lo, it was found to exist. So it's one of those given examples. It's like, well, mathematics showed it existed, and then we found it existed. But pretty much always you can find that if it either exists or if it doesn't exist. And if it doesn't exist, then it shows that the setting of analyticity about the principal and non-principal branches of these mathematical structures somehow makes this course of passage between them, and so then it's up to the superclassical to explain how that can be so, because otherwise it would eventually violate one of these other principles of the energy is conserved and the entelechy is continuous for these kind of continuum mechanics, these continuity laws as of above, these conservation laws, and implementing them, stronger and more thorough, making it so that it's not broken, about these running constants, about the algebraic derivations and the algebraic quantities for these numerical quantities, and in their continua and infinities, their wholeness and repleteness. So that's the usual kind of account of that there's always necessary to include the superclassical in mathematics, because otherwise it can be a self-contained, self-consistent account, but not complete. And so in the replete, it's presumable, well, even if this isn't then to necessarily so arrive at that it is as well complete, that it is at least replete compared to what then it would be possibly shown that different ideas of the modularity, like the linearity and the field or the divisibility, and then the dispersion or the distancing of things, they just wouldn't flat out contradict each other, and then make just a broken theory. So then thusly we can have examples in our theory of broken theories as examples, and as well to show how they're repaired, remediated by this re-Vitali-ization for measure theory and all the continuous and discrete and the discretization of things, discretization and the quantization of things, why it is so that these spurious twos and one-halves arrive in this stack of derivations and these kinds of things. So it's a continuum mechanics. Quantum mechanics is never wrong. It's a continuum mechanics. Plenum Press, New York and London. Exotic Atoms, 1979. International School of Physics of Exotic Atoms, 2nd, Erice, Italy, 1979. The second course of the International School in the Physics of Exotic Atoms took place at the Ettore Majorana Center for Scientific Culture at Erice, Sicily, during the period from March 25 to April 5, 1979. It was attended by 40 participants from 23 institutes in 8 countries. The purpose of this course was to review the various aspects of the physics of exotic atoms, with particular emphasis on the results obtained in the last 2 years. The course dealt with 2 main topics: A, exotic atoms and fundamental interactions, and B, applications to the study of the structure of matter. Section A was organized around 4 main subjects, briefly: positronium and muonium, quarkonium, baryonium, and neutral currents in atomic physics. So about the induced potentials and then currents is with regards to the neutral currents affecting kind of the susurrus of a sort, that being a word I saw the other day in a book by Paul Anderson, a collection of short stories, explorations about various interesting science fiction settings. that then as mentioned here, it kind of gets into the quarkian and the muonium versus in the positronium versus the quarkonium, about the ideas that these being substances reflect at least these four kinds of physics besides electron physics. Electron physics, muon physics, hadron physics is kind of like, well, taken that the hadrons are not really the nucleons, electrons. And then although that everybody pretty much gives to the electrons the orbitals and the relations to the atomic directly, and the neutrino physics, which help encompass that for each of these different kinds of tetradic quantities, and that could be mass, length, time, and distance. Those being kind of two things, or is in this sort of account. And then for the neutron, proton, electron, and photon, and then for things like the strong nuclear force, the electrical force, the electroweak, and then the weak nuclear force. These again, this tetrad of these forces or fields, or then the fields being as like the electrical field and the kinetic field, and the times, and then the lifetimes. These kinds of things help to show that in this kind of account, there's like four main subjects of this section A. In section B, a comprehensive account of the field of muon spin rotation was given. So spin gets into like spintronics and the skyrmion these days, because there's some more particle categorizations outside the standard model, and sometimes it's called the zoo of particle physics, because there's all these different kinds of varieties of things that are exotic in this kind of sense, from faraway lands and as of on their own account unique in these ways. Then the section B here gets into the muon spin rotation. And then and so the muon spin and the muon lifetime, it gets into continuum mechanics again, because a lot like the Stern-Gerlach apparatus and the reading from Feynman and Feynman setting up to show that he's like, well, let me set it up to show you that it's a particle. Now it's continuous. So here's how, when we stop and think about that, we can say it was a particle, yet you see that it is continuous, and I'm not going to have to break the curriculum for that to be implicit, so that your intuition won't be entirely unprepared, while at the same time we talk about these things in the middle, like the Laplacian and O.W. Richardson's account of the electron and charge, and the test particle and charge, and Leinard-Wiechert and such usual notions that kind of give a starting point in the linear, like the Galilean and these things, but then end up being partial and incomplete. So that muon spin encompasses at least two things. It's like, well, it's got acceleration and it's about rays and particles, and it's continuous. That the muons are basically uncharged particles, and then it is about the unlinear, as that though they represent the penumbral, the susurrus of the things, and otherwise the muon physics are where like everything that was like not fitting into the model got lumped in with muon physics for atomic molecular physics, and it's kinetic is what it is. So according to general relativity, this would be a primary particle in that. So the topics covered were muon motion in solids, muons in semiconductors and ferromagnetic materials, isotope effects of hydrogen, diffusion of metals, the chemistry of muonic radicals, problems of site determination, muonium-induced quadrupole moments, and muons in semimetals and quantum tunneling. So today, for the quadrupole moment, and then the tetrad and the virabine, or the four bind, that is about these, in reflections and rotations, there's basically two things. There's branches. And so then there's four. There's like, well, there's a branches, and then there's a branch at that too. And so trying to follow any one of those, then there's the multipole moments come out of that. So this is about the singular analysis here, and the singular integrals and these kinds of things. And analyticity is kind of mentioned above, and it is about a continuity of things when as something goes around a circle, at some point in time in the circle, it's pointing entirely away from any other given point in the circle. Or that for any other given point in the circle, there's some other point in the circle that's pointing entirely away from it. Yet by the isoparametric theorem and just this model of constant curvature and fulfilling the isoparametric theorem, still it comes around. And so the pole is like basically the axis through the center of that perpendicular orthogonal to it, the surface so defined. And so that's it's so different from just like 3 XYZ coordinates. They are linear. That the models of even polar coordinates and these kinds of things get into help defining why the multipole gets introduced, because it's just so different from the linear and the straight and for right angles, because it's rotational. And so then the idea here that gets into these things is when mentioning muonium-induced quadrupole moments, is that basically affects to reflect that it could go any which way. Otherwise, according to the analyticity, which is like it gives a direction, it gives a vector, it gives that a quadrupole is a modeling of vectors as a bivector, two vectors pointing in basically 90 degrees away from each other, or here is then in the higher order the quadrupole, and then what's called the multipole. And then getting into things like the infinitely many higher orders of acceleration, that's like an infinite multipole, vis-a-vis the monopole, and the idea then with regards to these systems, these fields, and how waves can be, in standing waves are established, and about the spiral waves and wave spirals for Kelvin and Helmholtz. This was one of these Reading Foundations episodes. That this is, again, helping to express that in the categorization of the cladistics of the phylogeny of these particles and their interactions and the models of them that keep it from breaking all its science, that these are things. And so are these still things today? Yeah, they kind of are. In fact, and that's also the language of them today, in as far as I'm aware. And so then things like the skyrmion and spintronics, that spintronics is a big thing today, about the magnetic monopole, which doesn't exist. It's like a singularity or a black hole from other parts of physics. It's at the same time, it's like, well, at some point in Born's restless universe where particles are never at rest, in their quivering, they go back and forth, and they either do or don't have gaplessness, and so no jumps or leaps. And so that entails requiring a continuum mechanics and the theory of the continuum mechanics, else that contradictions are readily derived. So that's why this account of the superclassical and thusly the more thorough account of continuum mechanics, and that it's a continuum mechanics, the entire theory, helps to make it possible so that otherwise these successful as they may be theories that can estimate and outcomes reliably, and then here that they don't, those get modeled by mathematical systems that contradict each other, that all gets resolved in a paradox-free reasoning. And so there's at least one theory where exotic particles, depending on how you look at them, are perfectly normal, and then it's a matter of model relativism in a sense that these things don't contradict each other mathematically and make it so that there's a universe that's not a universe at all. So it's one theory. A monoheno theory, a thea theory. The lecturers were kind enough to edit their notes so that we are now able to present the proceedings of the course. We would like to express our appreciation and gratitude to all of them for the effort they put into both the preparation and presentation of these lectures. The editors. Muonium, positronium by V.W. Hughes. Anomalous muon capture and lepton number conservation by B. Hahn and T. Marty. So the numbers like numbers of spin and numbers associated are whole and fractional numbers like 1 and 2, or a half, or 3 halves, or 5 halves. Things like these numbers assigned to the particles have the particles live in the field number formalism. So there's a field of physics' field, which means a space-time associated with a vector field atop it, a vector field of forces, and that it's all one field though. So just like a theory can be a theory of forces, then in physics today, or last I heard, physics is still a field theory to have all the fields together, because then that makes it possible to take things like a theory of two-dimensional kinetic action, vis-a-vis kinematics, and then into the three-dimensional. Then for things like electrical charge and current, induced potentials, potential theory, potential difference, electromotive force, and these kinds of things in its own field overlaid on the same map of the continuous reticulation of a space-time. Here, kind of separating time on the side for that space is a thing and time is a constant, and everywhere for these space frames and space frame spaces. That the field number formalism is like, okay, so at any given point in time, it's got a number. Any given point, it's just got a number for each of these different quantities. And so then at some point in time, there's given those, and then usually when it gets going up into the higher dimensions, it's like, well, we got to add another layer to the field number formalism and give it another number right there, and explain how it's related to all the numbers, the interacting terms of those, and all of its neighbors in the point and local, which is like right, their nearest neighbors. The global, their far away neighbors for the near field and far field, those being the usual terms, out to the total, which is like the Mach-ian and universally, and is like whether that's spinning or, and there's an anisotropy at all, or whether it's isotropic, which is the usual idea of one map that's a flat space-time, then at any given moment it's like so, any given instant it's like so, everywhere. Because all the usual theories evaluate the entire universe everywhere formally, quite a bit more entirely locally, and the SR is local. That this gets into why there's when there's this description of lepton number conversations or conservations. Excuse me if I kind of has switched conversations and conservations. That this anomalous muon capture and a lepton number conservation gets into the exchange and the conversion of particles. So the muons get converted as the numbers get conserved. Is this kind of thing. So for the energy and entelechy, that helps also reflect a kind of a dual and an interplay and an interaction between conservation and conversion. Duclos, a new measurement of the muon capture rate in liquid hydrogen. So this goes to show that whether these particles are real or vertical, and is with regards to being able to measure them at all. Because another usual idea is like, well, for a given particle, there's a kind of detector, and so if the particle reaches the detector, it's converted to another event, and so that's always conserved, and then we can say that this event arrives, which is usually an electron or photon. Something that can be detected by a voltmeter or a photon multiplier's output, usually, is the idea. Polarization experiments in the Godfrey-cycle by Grenache, parity non-conservation in atoms and molecules. So this PGH Sandars, Sandars, has parity non-conservation in atoms and molecules. So you got charge parity in time, and then with regards to that in like antimatter and these kinds of ideas, here's what's mentioned like the positronium, and these other kinds of concepts saying it's like, well, as an ideal, as something that's perfect, we got to give a name to it having that property and quantity, because the standard account has no way to even say it exists, but we're talking about it. So we can either say that we have to complete the standard model and show it's broken open, like the discovery of the Higgs boson does when it finds a doublet instead of a particle, for sure, and according to the data. But if you kind of squint and ignore the outside, you can just say you only see one particle, that this is still a way to talk about these things and giving them their own grounds in their fields and for numbers, and then being able to consider those the field number formalisms. Then the parity in reflections, rotations gets involved in the gauge. So the gauge is basically about torsion. It's like, why do we have a gauge theory when you say physics is a gauge theory? It's like, well, physics is a field theory, but then when trying to deal with non-analyticity and singularities in field theory, we just say it's a gauge theory. So then the gauge is just whatever defines the tensor that somehow keeps that real and analytic, meaning the continuous. Because otherwise, what we're saying is it's a field theory and it's a gauge theory. So physics today, to put together all these different kinds of fields and forces, that's why it's not just a force theory or not just a particle theory. It's not just quantum theory. It's not just relativity theory. It's a field theory, is what it, or at least 20 years ago, and it's still this case today. If you ask a physicist, it's like, well, what is the theory? They'll say, what's a field theory? And so it's all these other things as well. Chapter 2, quark atoms. Well, a quark is, you usually think of it as like a constituent particle of an atom, but think of a quark as an atom again, there's quantum chromodynamics and the color force, so supposedly by gluons attaching these quarks together, just like the nuclear force attaches nucleons together. That these quarks are supposedly smaller than neutrons and protons, that make this stoichiometric. That these quark atoms, I would think that would mean it's like, well, how about, that atoms are uncuttable? Okay, how about, that nucleons like protons and neutrons are uncuttable? They're atoms, atomos. Well, now we're just going to talk about when quarks are uncuttable. And it's just another layer beneath that of saying, okay, now this is fundamental, this is fundamental, this is fundamental. And so then to arrive at then why that's not just a continuum mechanics in extremis ad absurdum, ad infinitum, is that it is. And so then that's called technicolor. So the idea of quantum color dynamics was like, well, the color force is like, well, we're going to assign these forces red, green, blue, and they don't have an attachment or association to things. It's just purely qualitative. Okay, now, well, if you want, you actually have a dual tristimulus color space color model. They kind of are also qualitative. And so then technicolor is just the idea it's from a setting of film production or something where it was like, well, technicolor makes for better color reproduction in display media like film. And so we're just going to call it that. And what it means is it's quarks and quarks and quarks again, all the way down. So it's like about the same thing as infinitesimals in mathematics of theory, because there's no atoms in the complete order field. There's only atoms in something like iota values, and something like the signal reals. And after that, for these line reals, iota values, field reals, the complete order field, signal reals, analytic reconstruction. That's being always like not atoms. These are the kinds of things that I read from quark atoms that is going to be about quantum chromodynamics, and then something like the color force, and then the technicolor. The idea that it is quarks all the way down, turtles all the way down. Test of QCD with heavy quark bound states by Rafelsky and Violier. Baryonium, nuclear atom or color molecule by Chan Hongmo. And so these would kind of get into the ideas of this is where, again, discretization is ended. And so it's like, well, what's going on with these, with quark atoms? So the first one's kind of like about muons, fundamental interactions, muons and positronium. Second chapter here is about quark atoms. So it's like atomic theory redux is what it's about. And then it gets into, here's the chemical physics of mesic atoms and molecules. So the mesons are like the electroweak. So if the muons are like the weak nuclear force, then the mesons are kind of like the electroweak force. Now, I'll feel bad if I get something just so terribly fundamentally wrong as to ascribe these properties in any way that aren't actually accurate, but it's kind of like so. Because what happens is when something like the lepton gets assigned to be defined as something, whether or not it would be according to like a chargeless particle, or only to a charged particle. And so, like, about the photon, and when you have photons and electrons, it's like, well, which one of those is the lepton? Which one of it is, according to the number, which one is the force carrier of these kinds of things? That this is kind of an example then for the mesons. It's about mesons. So what are mesons and hadrons, and then with regards to bosons and fermions? So with all these being according to these forces and fields, then about the statistics and probabilities of the interacting terms, then they categorize particles into bosons for Bose. Bose was an Indian mathematician and physicist, most famous for Bose Audio, because the company that so resulted was Bose, from the theory of the acoustic and this kind of thing. So Bose made these statistics then to apply to these quantum states. And then Fermi, Enrico Fermi, was mostly, he's associated with radio and stuff like that. He's got different statistics. So these statistics and those statistics of the bosons, particles that obey or appear to obey Bose statistics, and fermions, particles that appear to obey Fermi statistics, are two different things. Then parastatistics are like these particles don't obey either of these things. And so then with regards to muons and mesons and leptons and hadrons, again, this kind of like, this is another tetrad of these things that get into why the particle physics gets involved, because it's using a very simple concept of the particle and the point for all these different interactions that could be, and according to physics, which is super classical. So that's just to explain. Then this gets into that. Atomic capture of negative mesons. New development in the study of mesic chemistry. Elastic scattering of muonic hydrogen atoms against protons. Status of experiments. Muon transfer processes from free muonic hydrogen and deuterium. Recent experimental results. Hydrogenic mesomolecules and muon-catalyzed fusion by Rafelsky. So see, long before chemically it's just a nuclear reaction or low energy nuclear reaction or cold fusion or Pons and Fleischmann, 1986. This is the idea that various events make for catalysis, kind of like it says, is muon-catalyzed for the reactions. So in chemistry, you have a model of reactions and their catalysis, and the way they give off or take in heat usually is the idea, according to then something like Zabotinsky reactions that oscillate quite about thoroughly in long-running oscillations and restitutions. It's about the structural and the molecular of these things. This just helps introduce that the interaction of these forces can make it so that particular configurations of experiment and energies of experiment have that then as those increase in size and in concentration or in regularity, or as well in the configuration and in the energy, just the amount or the inputs and outputs, that the running constants tent themselves up and make quite a giant big tent that under this circus tent of exotic atoms from 1979 are all kinds of physics, and these are real experimental physics. For the theoretical physics to explain that today the modern kind of like monoculture of the standard model, as it's usually called, the standard model of cosmology and the standard model of particle physics, is essentially lopsided. It's kind of it just goes to show that there's a wider account that takes in all of this kind of stuff together, and then to explain how that's so is usually resolves then these principles of like, well, it's got to be a field theory, it's got to be a gauge theory, it's got to be a continuum mechanics, and then for that to be so. So that's the usual kind of thing, like so. Chapter 4, or the fourth section, says muon spin rotation. So much like the first one was like fundamental interactions, got to muonium and muon capture and lepton number conversation. These are muons that are not spinning. So this is kind of the difference between muons that are linear and muons that are rotational, one says. So here there's a great account from the moment in motion bit about the world's turn. that it's long known since Aristotle, who's like, there is no unmoved mover, yet circular movement is eternal. Or like about fields, and it's like, why is this field theory a gauge theory? It's because like, well, something spins around and it would essentially become its own little world of these things. So this muon spin rotation then gets into skyrmions and spintronics, it's called. So spintronics is one of these ideas, is like, well, yeah, before we make a chip that's just electrical, to like get onto like photons instead, or even thermal pipes, whatever can use a model of change in an open system to model computation. For example, using electrons to flow everywhere at once because the potential is universally attenuated, or light to reach a bunch of equidistant particles, their endpoints, the pins, at once, because light travels at a constant, or for heat to like dissipate. You know, that the spintronics get involved even in electrical, in the effects in semiconductors, from bringing materials into the mix, that you can find about spintronics quite a bit today. And so when you hear about quantum computing or whatever, usually that's just like, well, it's simulated quantum computing. We've implemented, according to Mach-ian, an acoustic wave transducer, so we can compute a lot of solutions at once. Is that what qubits are? Is that what they're saying? Is like, well, yeah, kind of. And then, because the real quantum computation is, it would have to be defined by a very thorough account of like spin. Gets into spin is again another one of these numbers. It's just kind of like a count of how many times it's spun around, not like the rate it's spinning at every instant of time. See, because it's super classical. It's like past the atomicity. It's infinitely divided. These kinds of things. So the muon spin rotation then is this chapter. Muon diffusion and trapping in solids. So here, attenuation and dissipation are given as kind of like, well, this is least action with the least gradient. So oscillation and restitution is like, well, this is least action with the least gradient. And so this diffusion is a very usual example in models of gases, models of liquids, because the usual idea of the model of flow is of liquids. But there's always kind of like a liquid and a gas associated with any liquid or gas. And then there's vacuum and matter. And so then usually all our models of matter are clear, and then otherwise there's space. And so then everything else is kind of a liquid or gas, is like anything moving around that. And then there's the acoustic kind of in that as well. As an example of a space of configuration and energy of experiment, or configuration and energy of state, of the energy and entelechy. That's all one thing again. So muon diffusion and trapping in solids. This also evokes the scattering and tunneling. So that's usually about quantum electrodynamics and the S matrix, and it's for Feynman's quantum electrodynamics. And what it means is that so we got a grid. So how does this particle get in a straight line through this grid if it can never be at any intersection of the points, or it always has to be the intersection of the points, the co-sighting of these things. So that's with regards to the sighting of the things. How does it travel, if not in a straight line, that it results in the shortest distance? The scattering and tunneling matrix. And so scattering is basically how that radiates, and then tunneling is how that doesn't radiate. Or as with regards to that Huygens principle and stuff like that, that scattering is how it expands radially, and then tunneling is how it still goes in a straight line. So that the path integral of the formulations after Schwinger, and it's usually called the development of Feynman, but Feynman really put together the mathematics of Schwinger and this stuff from 5 or 10 years before that. That these are the kinds of things that get into this, well, what can we do then? Find out that, like, when we have the the embrittlement of metals by hydrogen, because like, well, hydrogen is just an atom, right? It's like, well, it kind of looks like a muon, you know, because then if you make a metal tank of hydrogen, it's just like, well, put hydrogen in it, and then come back later and hit it with a hammer, and it will break. Because why? Well, the entire structure of it changes because of these kinds of effects and things. Next section is hydrogen diffusion and trapping in BCC and FCC metals. So base-centered cubic, face-centered cubic. So these are the classifications of crystals as orthogonality and lattices, like Schläfli and Christoffel, they're given qualitative things. And then for things like N.J.A. Sloan and Conway, it's like, well, what if there's circles instead of squares? So you got, for mathematics, there's like N.J.A. Sloan and John Horton Conway and packing in spheres. And then there's also Christoffel and Schläfli, their numbers and qualitative settings for like its hexagons, or it's otherwise platonic solids that fit together and leave no other space about them. So like as a complement to the isoperimetric theorem, you know, it's a circle has always got the least amount of perimeter for the area, or so and so on, that the sphere has the least amount of surface for the volume. It has the least amount of the lesser dimension that encloses the most of the greater dimension. Then similarly, these lattice and things is like, well, how many faces does it reach that they're incident, and that there's nothing left over from that. So this is getting into like, well, what happens when how much per cubic what does this according to these? Teichler's light interstitial diffusion in metals. So the saying interstitial is the interstices are like the connections between. So when you think about a boundary between two things, you could think of it like Brentano and the boundaries, because in a theory of parts and a theory of sets, those are two different things. And so when interstices are between two things, it's kind of like the intercellular and extracellular matrix of a cell, like a biological eukaryotes, its cells. So like the phospholipid rafts or whatever that end up forming the cell walls, they touch. And so then when something's interstitial, it's like whether it actually crosses two cell walls or overall it just crosses one to get from one to another. And so that then there's whether the extracellular and the intercellular are two different things. Here it's kind of like that to get involved setting up the definitions. So like light interstitial diffusion in metals, whether that refers to the quantity of light or the weight of these interstices. Some aspects on positive muons as impurities in metals. So this is describing for alloys and the treatments of metals, like martensitization or quenching or vanadium hardening or otherwise the tempering of metals, and then also the alloys and the alloyification, if that's a word, of metals, and that the finishes also of metals affect resulting their material properties in given configurations and energies of experiment and over a long time. So these are also the experimental settings for material science. It's kind of like in this decade, there began to be all the like Skylab and all these experiments were sent up into space for microgravity research, and that's been kind of read here from the book about the Russian and American space programs and how those define what results were expected according to these settings. So that's one of these examples here. Is trying to figure out, it's like, why is that going to be so regardless of the surrounds? That it's fundamental and that it always adds up. So these are the kinds of things. Some aspects on positive muons, there are others, as impurities in metals. LAMPF results or LAMP results on mu plus diffusion in metals, mu SR in semiconductors, so mu usually micro, to the millionths, mu SR in ferromagnetic materials, so I'm not sure what that is just by its name there. Free radicals in muonium chemistry. So the radical generally represents a monopole, a point charge, not a discontinuity, yet the least otherwise of these things, or the most. So what I wanted to look at was about quark atoms, and just to see if that kind of reflected on the what later become called the Technicolor approach as after quantum chromodynamics. here's an example thing about the Godfrey-cycle. So the Godfrey-cycle is about kind of like, well, it's like an oversight. It's resonance theory is what that's about. Jackson, Tryman, and Wild, T-R-E-I-M-A-N, and Wild, W-Y-L-D. Calibrated results. The conclusion is there is no second-class axial vector current in beta decay, since B plus is approximately B minus. Fe over Fa is not larger than 1/10 of Fm over Fa. So this is just like, it was like, well, this is statistically significant, or lack thereof. On the other hand, the sum A minus and A plus yields Fe over Fa equals 3.79 times 0.48 over 2m. We'll use this determination of Fe in the determination of mu capture measurements. So according to these scales, and then like there's a retroplay is like, well, this kind of vanishes, but this other part kind of stands up because they're reciprocal. And so, well, we can't really measure this way, so just measure that the other way, or by its absence or vanishing. So that then at least, otherwise the mathematics would give nothing. It would have already lost all the analytical character. These ideas of the more thorough account is after the unlinear, say, but what is really the sum of potentials that makes it seem. See, there's something about page 111. Quark atoms, an experimental overview with quantum chromodynamics and charmonium. So this is another substance. So these aren't all particles. You know, it says exotic atoms, but then that's like, well, what about, we're talking about subatomic particles. So with those are not the usual ones. Then we have exotic atoms. And it's like, well, we're talking about atoms. But our molecules are put together in molecular structural chemistry. So those are put together as exotic molecules. But here it's just like at some point in time, they all just are like one thing, and it's a continuum mechanics is usual idea. Quark atoms. Thomas Appelquist, Yale University Physics Department, New Haven, Connecticut, 06520. Abstract. Some of the important theoretical issues and recent experimental results in the physics of heavy quark anti-quark systems are reviewed. On the theoretical side, special emphasis is given to unresolved questions in the use of quantum chromodynamics, QCD, to describe the lifetime of Q-bar states. So that's like the quark and anti-quarks, I guess it is here. The possible impact of recent experimental work on the pseudo-scalar charmonium states and on the upsilon states is discussed in a list of critical experimental questions which may be answered soon as offered. So the pseudo-scalar is part of usually the linear development and the Hamiltonian, and that being a system of linear equations that results in superposition and solving differential equations. So the pseudo-scalar then is like, well, it's like, well, that would be the shadow of it, or that it is intended to reflect between the scalar and the vector, that the scalar quantity is usually the inner quantity. But a pseudo-scalar quantity is like, well, it's two external quantities. And so sometimes when an inner product won't do, it's yet an outer product. And so that's all about the complementary duals and the usual notions of inverse. And it's much discussed here in earlier talks. Then the pseudo-scalar, kind of like the multipole moment, is like the pseudo-scalar is the opposite of the multipole moment. Yet they are each other. And so that's kind of what it's about. Introductory note. In preparing the lectures, I relied considerably on a recent review, Charm and Beyond, written by R.M. Barnett, K. Lane, and myself. It has just appeared in the 1978 edition of the Annual Review of Nuclear and Particle Science. A number of figures and tables were taken directly from that paper, which dealt with quantum chromodynamics and charmonium. So the quarks are defined in these various names, like up, down, top, bottom, charm, strange, quarks. And so then the charmonium is here, it's one of these particular things, like muonium or what was this, leptonium? But muonium, as from the introduction here, as was read, just to establish that these are these the exotic parts, but they're their own definitions and terms. Muonium and positronium. Positronium basically being the quantity that's like the positron is it's like it's got the mass of an electron, which has only got a charge mass ratio, but it's positive. It's the antiparticle to electrons. So not like the virtual particles or the partner particles or the super-symmetric particles. These are the antiparticles getting involved with these things, which are all simply reflections on perspective and projection of coordinate settings and singular integrals and differential systems together, and the differ-integro and integro-differ, and complementary duals and inner and outer products, manners of speaking. This contribution to the proceedings will not reproduce all the material of the lectures. Instead, I have tried to write something that is a kind of pedagogical companion to charm and beyond. So that would be usually kind of the technicolor is the idea. Whereas charm is like the last quark already. And also an updating of its experimental data review. The most important issues are stressed without reproducing all the detailed charm and beyond. Hopefully this will make it easier for non-specialists to get some appreciation for the main theoretical ideas and for the experimental questions being asked. There have been a number of important theoretical and experimental developments since the spring of 1978 when Charm and Beyond was completed. They bear directly on several fundamental questions, and I will discuss them and their implications as completely as possible. Introduction. So it's been a while since I've scanned through this, so I'll just read get some idea of the flavor of its language. Introduction. There's a great deal of evidence from experiments which probe the structure of hadrons at short distances that the strong interactions become progressively weaker as the distance scale is reduced. This is the asymptotic freedom. From deep inelastic lepton-hadron scattering and E plus E minus annihilations into hadrons, one can conclude that below distance scales of perhaps 1/10 Fermi, the forces which bind quarks have become weak enough to treat the quarks as non-interacting to a good zeroth order approximation. The interactions can then be taken into account perturbatively. So the idea here is that that's the scales and explaining why the strong nuclear force can also implement to be the explanation, to be the cause of gravity, because of fall gravity. So that the idea is that fall gravity, the concept, unifies the strong nuclear force and gravity, so that gravity is not left out of this field theory. It was already there, is the idea. And the idea that then the strong nuclear force doesn't hold together in the middle has the idea is like, well, it's mass and length and time and distance as it goes to infinitely small, that any one of those things that's any kind of classical scale entirely outweighs all these other ones and causes them entirely to spin, to lose in that vortex is what it is. That is what makes these things in these points. It is a singular analysis. So that's helping to explain a little bit. It's like, well, that can't be the model of things because we don't know what comes in and goes out. It's like, well, yeah, it can. It's just broken out all these different many ways. And then trying to figure that out is kind of thing. So then how that works and makes for like why the classical force model, for example, doesn't that it's not doing work for nothing, that it doesn't violate the classical expectation that electrons would naturally be attracted to protons and at least one of them would fall into the nucleus because they're sitting on that as a substance. These things helps us show that it's possible to have an overall kind of mental picture of all these different interactions. Then as the mathematics get developed, that still it's possible to see where in the mathematics that trade-offs were made, that approximations and these kinds of things. So there's these qualitative developments and these findings, like they find the experiment, it's like, hey, asymptotic freedom, give Solomon and Weinberg a bit of credit for the Nobel Prize then inherited by Grosch and Wilczek for happening to run this experiment that's being described here by Appelquist. That this is not so exotic anymore. This is a super standard model of these things. The important point does not, however, allow us to compute the properties of mesons and baryons composed of the usual U, D, and S quarks. These hadrons have a typical size of 1 Fermi, and at this distance scale, the quark binding forces have risen to their full strength. Perturbation theory cannot be used. In addition, and partly as a consequence, another complication arises. Since the quarks are confined to a 1 Fermi radius, they must, according to the uncertainty principle, have momentum components of at least 200, 300 mega-electron volts. But since the effective U and D quark masses are no more than 300 mega-electron volts, it seems very likely that ordinary hadrons are relativistic systems. So that's like today, it's like, and it's a doublet. So saying the relativistic systems is like this relativistic relativity of otherwise the absolutes and the constants that are in the whole universe reflected in a point. That's the usual thing. One is perhaps somewhat better off with the S quark. Mass of S is 500 megaelectron volts, but certainly for any hadron containing even one U or D quark, the combination of strong forces and relativistic motion has prevented any computation of its properties starting from an underlying theory. Well, maybe it's possible, and then just figure out how to suss it out from a number of different theories. All one theory. All right, that's kind of what I wanted to do today, was read this Exotic Atoms 79, Fundamental Interactions and Structure of Matter, as it helps show that physics has long had all these kinds of things. And like from O.W. Richardson, we already had at least 3 different models of electrical stuff that are obvious and available to experiment, like for Larmor forces, that each of these different Lorentzians still make for each of these different systems of energy conservation and continuity in the entelechy. Similarly, each of these models of particles and about the forces and fields model each other in terms of the mathematics that's somehow super classical, and it's always differ integro and integro different. It's always a fluid model, and it's always a gas model, and there's always pressure, and there's always attenuation, and these kinds of things. Entropy has both of its meanings. That is real in its physics. Well then, good day, gentle readers. Happy holidays, season's greetings.